Hi guys, in this lecture we're going to talk about arithmetic on random variables or making new random variables from old ones. So why does this come up? Well, if x is a random variable, well then we can, as a random variable, it has numeric output, and thus we can do math on it after we get the random value. And then the result of that arithmetic is a new random variable. So if x is a random variable, then x plus 1 is a random variable, 2x is a random variable, and x squared these are all random variables. Also, so that's one situation. The other key point of interest is that if we have two random variables, if x and y are both random variables, well, we can do math involving both of them. Like we can put them both in, and specifically, so it turns out one of the most interesting cases is just adding them together. So then x plus y is also a random variable. So let's see how this works. So suppose we have this random variable. All right, we can make a new random variable by, well, multiply it by 2 and add 1. And so to figure out the distribution of, so the problem is to figure out what the distribution of this new random variable is. All right, so we want to fill in the table k and then the probability that y equals k. All right, well, so really, in this case, all we have to do is take the values that x can be and transform them under this formula, and we get the values that y can be. So the smallest that x can be is -1. All right, so if x is -1, then y is 2 times that plus 1 is also -1. So -1. And x is -1 with probability 0.2, so then y is -1 also with probability 0.2. Okay. Now if x is 0, then y is 1, and x is 0 with probability 0.3, so that's the probability that y is 1. If x is 1, then y is 3, and that has probability also 0.3. And lastly, if x is 2, y is 5, and that also has probability 0.2. All right, so all we did is transform the sort of the k values to get what the corresponding values of y should be. And note that the probability that y equals 2, for example, equals 0. Right? In general, any value that's not included in a probability distribution table like this is just assumed to be 0. And it's fine if you have gaps, right? In this case, we skip 0, 2, and 4, since y can't be those values, because those would correspond to non-integer values of x. And as defined, x can only be these 4 integers. Right? Find the probability that a random variable z equals x squared. All right, so let's just begin doing exactly the same thing. So we have k, and then the probability that z equals k. All right, so we go through the values one at a time. Now it's off the screen, but hopefully you can still see it in your document. But that's right, the smallest is -1. We square that and we get 1. And that had probability 0.2. All right. The next value was 0, which squares to be 0, and that has probability 0.3. And then the next value was 1, which also squares to be 1, and that had probability 0.3. And then lastly 2, which goes to 4, and then that's probability 0.2 again. Okay, so this might seem super simple, but actually there's a little subtlety going on because the table that we've written down is not a valid table. And why isn't it a valid table? Well, because we have this repeated value, right? So repeated value. And so this does not, we have 1 in 2 different places with 2 different probabilities, so this table, as it's written, makes no sense, but it's actually really easy to fix this. All this means is that the probability z is 1 if x is -1 or 1. Right? There's 2 ways that z can be 1. And x is -1 or 1. So we simply add those probabilities together. So all the times that 1 occurs, it came from different values of x, and so we can just add these probabilities together to get the total probability that z is 1. So our final table is k, then the probability that z equals k. So our smallest value is actually 0, then 1, then 4. And then we have the probability of 0 is 0.3. The probability of 1 is 0.5, and then the probability of 4 is 0.2, right? So this looks slightly different than our original one, more so than our first example where all we did was change the k values. And of course, after we do this, the probabilities should still sum to 1. Still sum to 1. Right? You know you made a mistake somewhere if you get a probability distribution that doesn't sum to 1. Okay, so on to the more complicated situation, which is now we have 2 random variables. So we're going to take w to be basically the same as x, but just independent from x, and compute the probability that x plus w equals 0. Right. So adding random variables is actually kind of a key thing. We've kind of gone through this logic before in specific examples, but let's just go through it carefully and systematically. So what I want to do is list the possible values for x and w, and then we'll figure out all the different ways that they can add to 0. So we have x can be -1, 0, 1, or 2, and w can be -1, 0, 1, or 2. Now to do this systematically, I'm going to start with the smallest possible x value. Right? So the smallest possible x value such that the sum is 0, right? And that corresponds to -1, because if we take x is -1, then we can take w equals 1, and we get a sum of 0, right? So that's one way that their sum can be 0. So we have probability x plus w equals 0. So one way this can happen is, well, what's going on, is if x is -1, w is 1, and they're independent, so the probability of that happening is just the product. Probability x equals -1 times the probability of w equaling 1. Okay. And now to figure out all the ways that this can happen, what I'm going to do is increment x, so increment x by 1. Now since the sum needs to stay the same, it needs to be 0, I have to decrease w by 1. So I get my next pairing. So plus the probability that x equals 0 and the probability that w equals 0. So the probability that x is 0 and w is 0, which is again just the product since they're independent. Okay, and then I do this again. I increment one and decrement the other, and so in this way I maintain the same sum. So this is plus the probability that x equals 1 times the probability that w equals -1. Right. So now I would like to keep going, right? I can increment x again, but I can't increment w. because it falls off the edge. So so I know that these are all the ways that the sum can equal 0. And so we just plug these probabilities in, right? So this equals 0.2 times 0.3 plus 0.3 times 0.3 plus 0.3 times 0.2. And I believe that equals 0.21. Right? So that's our answer. Now, if we wanted to find the probability distribution, right, we'd have to do the same process for all the possible sums that x and w can have. That's essentially what we're going to do in the next example. All right, so this example is a little complicated, but we'll work through it systematically. So what is the probability distribution of the sum of 2 6-sided dice and 1 4-sided die? So there's 3 die here, so that means 3 random variables. So I have 3 random variables. So we could say x1, x2 are the values of the 2 6-sided die. And then y is the value of the 4-sided die. Okay, so 3 random variables, and we're adding them all together. Now, to make this simpler, what we're going to do is we're going to look at the probability distribution of x1 plus x2. So we're going to sum them first. So sum x1 plus x2 first, and then add that result to y, then add y. And the reason I'm doing this, partially because adding 3 things together at once is actually really complicated, a little more complicated, and also we know what the sum of 2 die together is already, what its probability distribution is. So if we have k equal, so k, and then the probability that x1 plus x2 equals k. Right, this is just the sum of 2 dice. We know what this equals. We've sort of gone through this before, right? It can be anything from 2 through 12. And the probability is 1 over 6, 2 over 6, 3 over 6, 4 over 6, 5 over 6, 36, all of these. And 6 over 36. Then back down, 5, 4, 3, 2, 1, and all over 36. And I'm not simplifying fractions to make the pattern of values clear. If we scaled it by 36, right, it's just linearly increasing and then linearly decreasing. And then our probability distribution for y, okay, and then the probability that y equals k. Well, there's only 4 possible values, so we have 1, 2, 3, and 4, and they're all 1 out of 4. Right. So now we can, using these 2 tables, we can look at the probability that x1 plus x2 plus y equals k. That should be inside the parentheses. Right, so the probability distribution for the sum of all 3. Alright, so, well, what's the smallest value? The smallest value is 3, and the largest value is 16. So we have all the values 3 through 16. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Alright, we're just going to do a few of these. If you could do one or two that I don't do, you don't have to fill in the whole table. Right? An incomplete table is fine. So, because this is just a lot of repetition. But if you should feel like you could fill in the table for any value you wanted to, right? That's the important part of this exercise. Okay, so let's start out with 3. That's the simplest. Well, 3 and 16 are the simplest, but we'll start with 3. How many ways can the sum equal 3? Well, it can only be 3 if x1 plus x2 is 2 and y is 1. So, right, there's only one way that can happen, and they're independent. So this is 1 out of 36 times 1 out of 4, which equals 1 out of 44. Sorry, 1 out of 144. Okay. So let's raise it up a notch in complication. So how many, what's the probability of getting a sum of 4? Well, I'm going to use the same strategy we used before. So we'll set this one to be the lowest possible value while still getting a sum of 4. So that's 2. So we're going to set x1 plus x2 equals 2. And then what does y have to be? Well, y has to be 2 so that the sum is 4. Okay? So that's one way this can happen. And that is probability of happening of, again, 1 over 36 times 1 over 4 is 1 over 144. Plus, now the next way this can happen, I'll increment this by 1 to get to here, decrement this by 1 to get to here. So now it's 2 over 36, right, times 1 over 4. So this is plus 2 over 144. And that equals 3 over 144. Right? Okay. Let's do 5, and then we'll skip to 10. All right. So for 5, again, we could start with 2, and then we would need 3 over here, right? So we'll have 1 over 144 plus, so again, we increment this one, decrement this one. Now we have 2 over 144, 2 over 144, and again, we increment this one, decrement this one, and then we have 3 over 144 plus 3 over 144. And that equals 1 plus 2 plus 3 is 6 over 144. Okay, so let's do 10 now. How many ways can we get to 10, and what are their probabilities? I'm just going to use a different color than trying to erase. Alright, so if we had x1 plus x2 equals 2, then y would have to be 8, which it can't be, so that can't happen. So the biggest y can be is 4, so the smallest x1 plus x2 can be is 6. Right, so we have to start here. This is our smallest. 6 and 4. And then we'll increment one and decrement the other. So this has so 6 and 4 is a probability of 5 over 144. Plus, we'll increment this one to 7, decrement this one. And this is probability 6 over 36, so the total probability is 6 over 144. In, increment, decrement, and we get 5 over 144. And then the last value is 9 and 1. So we have 4 over 36 times 1 over 4, so 4 over 144. Equals, so 5 plus 5 is 10, plus 6 plus 4 is 20. Over 144, of course. Alright, now we could do the same thing for the rest of the values, and now I'm just going to tell you what 6, 7, 8, 9 are. So 6, we get 10, I believe. Yeah, 10 over 144. 7 is 14 over 144. 8 is 18 over 144. And then 9 is also 20 over 144. Alright, now I'll just tell you what they all are. So this is basically because all of these, both of these are perfectly symmetric, so is their sum. So we have 1, 3, 6, 10, 14, 18, 20, 20, and it just counts down, 18, 14, 10, 6, 3, 1. And of course these are out of 144. Now let's look at what that distribution looks like. So this is the histogram for it. Oops, I have this already here. That shouldn't be there. Giving the game away. It looks like this. And now you kind of might notice that this looks, well, it looks kind of like a familiar curve, right? Which is the one I just erased. And now it grows by, it grows a little slower at first, and increases, and then levels out, and then is symmetric like that. Right. Now, so this looks like a shape you probably are familiar with, which is the bell curve. This looks like a bell curve. A little like a bell curve. So why is that? Why would that be? We just rolled 3 die and their sum ends up the probability histogram for their sum ends up looking like a bell curve. So what it turns out is that the more random variables you add together, so I'll just say this very sort of imprecisely, but adding lots of random variables together always results in something that looks kind of like a bell curve. Always results in a bell curve like shape. And this is really why bell curves are so important, and we will study them in just a little bit in this class. A little bit. We'll study them a little bit. Yeah. All right. So that's all for now. See you in the next video.